uh, let's see how many stragglers trickle in. Okay, time to start. Happy New Year. Happy to see all of you. Well, out of everybody who's taking EML, which are still like roughly 200 people, I think we're roughly at a quarter right now. So also to the others, welcome. I guess you're going to be looking at this over the stream later on. I hope you survived the Christmas break very well. I hope you didn't miss us too much. We certainly did or didn't. What should I say? I didn't miss teaching so much. I enjoyed a teaching-free few weeks, but I'm also happy to restart right now. Good. Before I officially start the lecture number 8, where we go beyond linearity, I want to make a short, well, not even an announcement, but more I want to share some of my thoughts based on a number of emails that I got from some of you. As you know, the exam is coming up, right? And this is why you are here, why you're doing the assignments and all that good stuff. But maybe you are also a bit worrying about, okay, how does this now work with Corona? And maybe you are here in Saarland, maybe you are not, et cetera, et cetera. Yeah, we also worry. If you ask me as a person, do I think that we will have a regular in-person exam on the advertised dates? Well, maybe. I can't tell for certain. I can't tell for certain. And that's at the same time, when I wear my professor cap, the only reasonable thing I can say is that, okay, well, it is announced as it is, and we're just going to go forward, and well, we will make changes when necessary. The main problem being is that neither Professor Valera nor myself can just decide, oh, you know what, we go to an oral exam, or we change the dates, or we give everybody an exception, because that's going to make everybody's life horrible. It's going to make many things unfair, not just within the course, but also across other courses. So the only thing that Professor Valera and myself can do is right now wait and see what the policy of the university, respectively the computer science department, is going to be, and we're going to follow suit. If I take off my professor cap, I think the exams will be postponed until a moment where we can actually hold them in person here on campus. That's what I think, is what I expect. I can't make any official statement right now, right? So you cannot, I mean, even if this is now recorded on YouTube, you cannot take this as an official statement that things will be postponed. I simply don't know, right? I'm not wearing my professor cap. We have this obviously in check. We will be in touch with you as soon as we hear more. But for now, formally, we just carry on as if there is no Corona and everything just proceeds as normal, right? And for you, I mean, please do continue making the assignments, prepare, let's say, as if the exam would be, I think, somewhere in February, right at the top of my head. And yeah, maybe it gets postponed, but if you already study, it will be super easy to restudy a bit later. And let's hope that Corona disappears very soon and that our only association to Corona may be the Mexican beer, right? And that's good. Okay, that said, I put on my lecturing cap again. Once again, welcome to the Elements of Machine Learning. Welcome to the 8th lecture thereof, in which we are finally moving beyond linear models. And so far, you may have wondered, I mean, oh my God, it's 2020, by now it's even 2021, and they keep on talking about linear models. I mean, for crying out loud, right? Everybody's doing deep learning, doing cool stuff, reinforcement learning, whatnot, and we are studying linear regression. Yeah, well, that is actually, I mean, all by design. I mean, that's not just because this happens to be the order in the book that we're following. We chose this book, right? So it's our choice. As you will see today, and I think that this lecture today is one of the one that I most enjoy, and I think the one that will hopefully click many concepts that you've seen in the last 7 lectures, all of a sudden in a way like, hey, wait a second, it all made sense, right? They were not just yapping about. So please do pay close attention, and then at the end of the lecture, you'll hopefully see what I meant in that. Good. Yeah. It's also the 7th of January, but that is not so important. Moving beyond linearity. How are we going to do this? Today, we're going to discuss 4 different methods. I mean, yeah, if you count really luxuriously 5 or even 6, but I have 4 main classes. I mean, that's not necessarily following this ordering, this numbering. The first would be let's do polynomial regression. Right now, we just simply had every predictor in there linearly, right? So we had our x1 or x2 all the way up to xp. We put some coefficient in front of it, and that was our predictor, right? I mean, that's perhaps we had a regularizer to tame the coefficients a little bit, but that was that. We already since high school know about squaring and cubes and whatnot. Why not use that? Well, that is already the key idea in polynomial regression. So we'll be seeing that in a few slides on how to incorporate this and make our methods way more powerful than they were so far. The next method, that's a bit of a, well, this one that I normally would not really give a number, but in the book they dedicate a chapter to, or a section to it. Let's use step functions, right? I mean, if we have our input domain, right? I mean, x can take a value between, let's say, 0 up till 10. We could have, well, one linear function of it, or we could say, you know what, we're going to use this function if x is between 0 and 5, and between 5 and 7 we use that one, and between 7 and 10 we use the third one. Then all of a sudden you have a step function. It's not linear anymore, right? You can adapt to specific regions within your input domain, and that's which gives you a lot of power. Also a lot of headaches, but that's for a later moment. Now, the third in this list, this is by far my favorite, and that's this is well, one of the things that I have to admit, before I started teaching EML a few years ago, I knew of them because I was also taught these things when I was taking these types of classes, but I had forgotten about them. And when I then went over it, like, splines are amazing. I mean, that's I'm not going to go into too much detail right now, but essentially they, in a very cool way, combine polynomial regression and step functions such that you arrive at something that, well, does not give you a headache and actually gives you something very, very powerful. Now, splines by themselves are cool, but you can make them even cooler by smoothing them. Okay, we'll see about what that is in a second. Then this is essentially the real third method, you know, under my counting. The first one being polynomial, the second being splines, the fourth one being a local regression. You've already seen for classification and the likes that these k-nearest neighbor methods, right? I mean, even though they are stupid, right? I mean, there's not really any math or theory behind them. They work remarkably well. If you choose k in a smart way, they work remarkably well. I mean, almost unfairly well. And well, that is an idea, or let's say that we can, or an approach we can steal. We can just do regression just on the k nearest neighbors. And well, then we call it a local regression, right? Because why not call it k nearest neighbor regression? Well, yeah, just to make it more exciting, I guess. But that is the core idea in local regression. As you will see, this also works remarkably well. And then the one that is on this slide, not even numbered, but I would call method number 4, are the generalized additive models, GAMs, with an M, not a GAN, as some of you who looked a little bit into neural network land may know, right? But a generalized additive model sort of combines all of the above, and well, we have a lot more magic at our disposal. But that is for the end of today's lecture. And let's first start simple with simple polynomial regression. So there we go. We have here first the standard linear model as you know it, right? And I mean, either you have come to love it or you have come to hate it. I mean, that's both are equally fine with me, but you know, as long as you know that this is a linear model. As you see here, we use xi, right? I mean, that's so predictor x directly. I mean, we just take its value at face value, and there's a linear factor here. There's the intercept. There's some noise. That's that, right? I mean, that's now. Polynomial regression is nothing more than taking the value of x, right? This is just a simple linear regression. We only have one x. And what we do is we have here the same one. This is just basically we raise to the power of 1. We can also take the square of x. We can take the cube all the way to the dth dimension, right? Where d is then, well, the degree of the polynomial that you or the user somehow needs to choose. And the cool thing is that right now, if there is indeed a polynomial relationship, right? Let's say there is a quadratic or a cubic relationship between x, right? Let's say it's quadratic. This means that the linear model, it can't really capture y as well in terms of x as it kind of should be able to, right? Because it's only linear, right? And if the relationship is truly quadratic, right, it can't, I mean, poor little model. Whereas this one, if at least we have a degree of 2, then what we just need to find the right coefficient for this one. And well, this coefficient could even be 0, and all of these could be 0, right? And we have the perfect quadratic relationship between x and y. Amazing, right? I mean, that's okay, cool. What is now even cooler, if you think of it, and this is the moment where, let's say, everything should start to make sense. If you look at this thing, on the one hand, yes, it's polynomial, right? I mean, we have x squared, we have even x to the power d. If I would tell you this is actually it's just a linear model, then, well, after perhaps half a second, like, okay, what the hell is he talking about? After this half a second, like, yes, this is just a linear model. We have beta naught, right? I mean, just the intercept, I mean, as we had before. We have beta 1 and x, just like here before. Then we have a beta 2, okay, fine. And this x to raise to the power 2, we could just pretend that is just a different predictor. We could just call this one, just strike it through, just call it x2, right? Predictor 2. And then this would be predictor, well, xd for all I care. Because multiple linear regression, we all know how to do, right? I mean, then we just have multiple x's, right? Multiple predictors, and we know how to find the coefficients. That's exactly the same thing as we have here. It's just that right now we immediately defined that this pseudo x2 is actually x1 raised to the power 2. There's essentially no difference between multiple linear regression and polynomial regression or linear regression, right? It's basically the same thing. You can use exactly the same machinery to learn all these coefficients. But the only problem is that we went from having to learn only 2 coefficients in the pure linear case. We now, with just one real predictor x, we now have to learn 1, 2, 3, well, d plus 1 coefficients. So we have more parameters, and as you know, well, with more parameters, things become more difficult. We need more data. So yeah, it's not that trivial, but the machinery is exactly the same, right? Linear regression was the right starting point for this lecture. Now, which degree for your polynomial should you choose, right? I mean, how should you choose d? Well, you will want to choose d not too large. And first of all, I mean, if you choose d very large, you're going to have incredibly many coefficients. It will be very difficult to tune them all to the right value, right? I mean, that's the one thing. So we don't want to have the cursor dimensionality biting us in the back. Obviously, we also know if you have n data points and you use a polynomial of degree n, it becomes so wiggly, you can make it fit through every data point, right? It's just possible. And that's, so you definitely want to choose d smaller than the number of data points. Now, in practice, you don't want to go really much beyond 3 or 4, because then it becomes really squiggly, and it becomes squiggly, especially at the ends of the domain. I'll show you an example. And we again have the wage data. I mean, let me show you like here. And what we have now here, this is the age of somebody, and this is how much money they currently make per year, right? I mean, and all the dots. I hope that you can see them. I mean, I didn't have time to rework this plot completely into PowerPoint yet. I had other things to do during the Christmas break. And as you can see, if we just do polynomial regression, this is a 4th degree polynomial, right? Yeah, this is the dark blue, the solid blue line. This fits it quite well, right? I mean, that's pretty cool. Now, if we were to ask ourselves, where in the range, right, in this plot, do we trust this line, this prediction most? Well, obviously, the answer should be, well, we have the most data points, where the fit is the best, right? I mean, that's and let's say the confidence that we have in a prediction that we can quantify and we can show with a 95% confidence interval or confidence band. And that is what this dashed line is. This is the range that if we actually predict, for example, for an age of, so I'm almost 40, so I'm here, right? I mean, I should make a little bit over $100,000, and that, well, that's nice. Maybe I should move to the US. And as you can see, I mean, the dashed lines here are quite close, right? So basically what this analysis says, okay, you can trust in 95% of the cases, right, that the prediction I make around this, that is going to be within this band, right? I mean, that's so apparently lots of people around the age of 40 make that much money in the US. What you also see is that here at the end, these bands, they start to widen out, they start to taper out, right? I mean, that's makes a lot of sense because look, we only have, I mean, how many? 1, 2, 3, 4 people that have an age of 80, right? I mean, that's and only a few at 80, what is it, 70, 77 or something like that. We have very few data points here, right? And that's so obviously we should not trust our model to make a reliable prediction at these ends, right? I mean, that's, this is what you see, that the confidence bands, they start to taper out. How do you compute such a confidence band? I'm not going to show this in this slide, nor on the next one. I'm just going to simply point to the book. I mean, that's essentially what it comes down to is you simply reuse the machinery that you've been using to estimate the confidence intervals for the parameters, beta naught, beta 1, and so on and so forth. And we can use those estimates to get a confidence band also around the prediction, right? So it's basically a confidence of the predicted value y. I'm just not going to skip those details because really just read that over, play with it. I mean, it will probably be one of the assignments as well. Beautiful tool, we're just reusing stuff again, right? Now, what you already see is that because here at the end, we have little data points, that is in this case because we don't have so many, well, people beyond 80. But even by definition, we're going to have the fewest data points at the ends of our domain, right? Because we're at the end of a domain, we don't have data points beyond. Naturally, right? I mean, that may almost seem like a play of words, but obviously there is no data here, otherwise our domain would be larger. That also means that actually we have no clue how this line should continue, right? Could be that it should go up. I mean, that's maybe it should go down, but I don't know, right? We don't have data. There's simply nothing sensible that we can say. Now, this is a degree 4 polynomial, right? And that's supposed to we would have fitted a degree 40 polynomial. Well, you can even just if you think of a cubic or a quartic polynomial, it's super squiggly, right? And especially at the ends, it sort of shoots off in whatever direction it wants. And that is exactly the problem also here. So if we would have chosen a degree many polynomial, the direction in which it shoots off, completely arbitrary. So the chances that you can trust it at the edges of your interval, right, your domain, well, they're not good. Don't put any money on that, right? And hence, A, try to use a degree that is relatively low, and B, compute these confidence bands to see where can I trust my model somewhat. To make a very short aside, I was not planning for this, and I know that I should not do this for the interest of time, but one of the main problems that you have if you apply, let's say, the more advanced machine learning tools that we have at our disposal, kernel machines, deep neural networks, all that jazz, right? I mean, they're really good at predicting, but they're generally really, really bad at telling you how confident they are or how well you can trust them, right? So essentially they could, in theory, squiggle their way through the data, right? And make very good point predictions, but you would never know where are these dashed bands. And in the end, well, so if this would be your model, you know that for the range of 30 to, let's say, 60, you can quite trust the model, right? I mean, that's, and above 60, well, okay, let's not put too much money on it, right? I mean, that's, but without these dashed lines here, okay, it's just a gamble, right? I mean, that's, and that is one of the problems with many of the, let's say, the state-of-the-art machine learning models. They're very good at getting this solid line, better perhaps than this 4th degree polynomial regression, but you never know, well, how far off their prediction might be. So you don't know how, if you can trust it. Good, okay, that aside, I mean, that's, I wasted already way too much time on this, but I hope this was somewhat didactically useful. One thing that we can see from this plot, besides the pretty blue lines that we plotted, that there are people that make, well, if you call $200,000 a reasonable amount of money, and you have people that make obscene amounts of money, right? I mean, that's, or in the words of the book, you have high earners and low earners. Well, if in a few years you make $200,000 a year, right? I mean, that's, and you call yourself a low earner, then I don't know. I mean, that's, I will stop to respect you, right? I mean, you're not a low earner, but you could ask yourself that, okay, can we perhaps predict if somebody is going to be a low earner or a high earner, right? I mean, this is a classification task, binary classification. We know that we can use essentially the machinery of linear regression to do classification, right? Logistic regression, right? I mean, that's logistic regression was essentially linear regression, well, with a bit of extra magic on top, right? I mean, that's you've seen this, you know how it works, you played with it. Can we do this with polynomial regression? Yes, of course, no problem. That so the standard linear model is exactly as it was, right? I mean, that's what polynomial logistic regression. Normally, we would not have this term all the way up to here, right? But now we just have more coefficients and more terms, both in the numerator and the denominator. There we are. Nothing changed. Nothing changed, right? I mean, that's but of course, a lot of things changed because the fit that this model within the exponent can have on the data, it is much more expressive. It can get much more out of the data than just simple linear regression possibly can, right? That we have more degrees of freedom, we are more powerful, and hence the predictions that we can make are potentially much, much better, right? And that's so if the dependencies in the data are nonlinear, right now we have a chance of grabbing them, whereas previously it was just, well, yeah, very unlikely to work well. Okay, so let's go again to the wage data. Up, there we are. And as you can see, I mean, that's so if we now look what is the probability for earning a shit ton of money based on age, then the probability, that is the blue line again. Well, this is just plain logistic regression, right? I mean, as we've seen it. But it can take all sorts of fancy shapes. This is great. But, again, we've plotted the confidence intervals. And as you see, I mean, here, especially at the ends, when, well, they go crazy, right? Basically, they say that, okay, if you're 70 or if you're 80, and you could either make nothing or you could make, well, it could be a very high probability that you make a lot, right? I mean, basically, I have no clue, right? It just throws its hands up in the air. I mean, that's why does it do it here? This is to do with the flexibility of the polynomial, right? I mean, we don't really know where the line should go. Plus, if I now quickly go back to the previous slide, we simply don't have anybody in this age group that makes a lot of money, because probably they're all retired and it's just been savings, right? I mean, so yeah, that is what you now get here. Basically, the prediction goes completely, I mean, up, right? I mean, that's, or let's say anything is possible. Also shows why it's so important to always look at these confidence intervals, right? I mean, you always need to ask, when can I trust you, model? And that's, and the model, I mean, sometimes it gives you an answer, sometimes you need to torture it a bit. Good. Let's continue. I mean, that's that was polynomial regression. It was essentially all that I had to say about it, right? Because it's just linear regression, but we all of a sudden have a few more pseudo predictors, right? I just used X multiple times, namely D times, and then X2. I can also use a D times because simple linear regression, right, with just one X and one Y, that we can do now with polynomial. Exactly the same holds for multiple linear regression, right? So if we were to do multiple linear regression with X1 and X2 and X3, well, we can also do this polynomially. We just expand X1 to X1 and X1 squared and X1 cubed. And the same thing with X2, just plain and squared and cubed, and so on and so forth, right? And that, so we basically just pretend that we have many more predictors than we actually had, and we just generated them ourselves. Okay, good. That's that. Now we can properly go to step functions. Step functions are, well, friends don't let friends use step functions, right? Plain, but I do need them to explain the next useful approach. So what do we have? I mean, that's, we have an input variable X, right? I mean, that's, and I'm now going to, and this is the domain of X, right? This is value 0, and this is, let's say, the maximum value, right? Let's say, if we stick with the age example, this would be age 0, and this would be age, well, if I say 80 is the maximum, that is a bit I mean, already many of your grandparents will probably be beyond this. So let's say 150 or something like this, right? I think then we're quite safe. Now, within this age range, we can chop it up into bins, right? I mean, into chunks, where you say, you know what? Okay, from 0 up till 18, right? These are then kids. From 18 up till 30. I mean, I don't know. I mean, that's older kids. 30 to 40. I mean, that's play pretend adults. 40 till 60 adults. 60 to 150. I mean, old people. Something like this, right? I mean, that's now these age points that I just identified, those would be my cut points, right? I mean, that's, and I chose, I forgot, I already miscounted, I mean, I think 4 or 5, but we have a number of cut points. Now, what we can do, very simply, I mean, it's trivially, we can basically determine for a given data point, in which category do you fall? In which bin do you fall? I mean, are you 17? Yes, okay, you fall within the bin 0 to 18, right? I mean, that's, so if my first cut point is 18, right? I mean, that's, then the dummy variable C0 or category 0, right? I mean, that's basically corresponds to, the I means an indicator variable. This one will also only return 1 or true if the value of x is below the cut point. So if you're below 18 years old, right? I mean, that's, then C1, my category 1, in this particular case was, what was it? I think between 18 and 30, right? I said, I think you're a play pretend adult or something like this. I mean, that's, or an older kid, right? I mean, so only for when x takes a value that is larger or equal than 18, but smaller than 30, okay, then C1 will have to take a value of 1, right? I mean, that's, and so on and so forth. So this way, this means that for any actual individual, only one of these dummy variables, right? I mean, that's, they will take the value of 1 and all the others will take a value of 0. I mean, that's, in the literature, we also often call this a one-hot encoding. So those of you who already know this, aha, and those of you who don't know it, I mean, forget about that immediately. Okay, so this is basically the constraint that satisfies. There's only one of these constraints, only one of these C's is going to be 1, right? I mean, out of all. Okay, so what can we now do? We can now play pretend that we throw away x and we only have these indicator variables, right? We don't have one x anymore. No, we have k values for c. We have c0, c1, and so on and so forth. Well, and that many of them will be 0 and only one of them is going to be 1 for every individual. That is just a happy coincidence. We essentially have now k new predictors. And if we just have k predictors, we can do multiple linear regression, right? No problem. We just do linear regression again. So which now looks like this. We want to regress y, we have our intercept, we have beta 1, which, well, just takes, right? I mean, that's it now doesn't work directly on x anymore, but it works on c1. This one works on c2 and so on and so forth, right? We can just do plain, so very simple linear regression in that. Okay. What does it mean? So yeah, B0, beta 0 is essentially the average for people, in this case, with an age below, well, in my example, people that have not been born yet. In this particular case, it would be the average for people below the age of, I think, 18 here. And then for each of those bins, right? So we will have, if somebody is in this interval here, so now I just stick with the example on the slide, so forget about my example now. Then essentially the coefficient beta 1 is going to be the increase in average income over people, well, here on the left. And there's nobody here on the left, so it's basically like a play pretend kind of thing. So it's always the addition to the overall average, and that's okay. And as you see, we basically just put lines, flop, 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 right? I mean, that's and within each bin, you have a linear prediction. Often this will turn out to be just a line, right? Just literally a step function. I mean, that, but the shape of the function, whether it's truly a step function or not, that depends very strongly on how we force the shape of this line to be. Does it need to be flat? Can it be? Can it take other shapes? Right? Can it be wiggly or not? That's already a step towards splines. Okay, so step functions. Very simple, right? This is just for the regression. Then you can ask, okay, but I mean, can we also do now logistic regression using step functions? Well, yeah, sure, of course, why not? Because it is just linear regression, right? I mean, that's there's nothing special about it. The only thing is that right now, instead of just having beta 0 and beta 1 just with x, now we have beta 1 with the first indicator variable all the way up to the kth indicator variable. Nothing spectacular, right? I mean, that's, and again, just like in the previous case, we can draw the confidence intervals and, well, we can do the prediction here like that. Okay, very good, very nice. I mean, that, now, what should be the question that already when I started about these cut points, right? I mean, in these ranges, how do we choose them? I mean, how many? And where do we put them, right? I mean, that's so for ages, I mean, what I just proposed might make sense, right? I mean, up to you're 18 years old, you don't make so much money, then perhaps you're still studying, blah, 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 right? But of course, this was an arbitrary example. I mean, that's, we need to place these cut points very, very wisely, very smartly, right? If we place them in the wrong point, the model, well, what we call, misses the action, right? I mean, if we were to just cut this whole data into just, let's say, 2 bins from age of 18 up till 50 and 50 up till 80, would have a pretty bad model, right? I mean, that's because the action in this particular case is exactly in this area, right? I mean, that's somewhere between 30 and 65. That's when people make money. And if you include too many people, let's say on the left side, which don't make much money yet, then your prediction for this whole bin will be bad. And if you include too many people who have already retired, then your prediction for above 50 will also be bad, right? I mean, that's so somehow where to put these cut points, we need to choose that very wisely. Okay, this is where one of the next methods, I mean, will come in. That's but for now, I'd like to also just ponder a little bit on how on earth would you choose these cut points. I can already give away how you choose the number of cut points. And that's hopefully you already see the answer yourself. I mean, cross-validation, right? I mean, that's in almost all cases in machine learning, but definitely within this course, if you need to make a choice for a parameter, cross-validation, right? And that's, it's just use the data to inform you what is the most likely a good choice for generalization. Good. Let's see. Yeah. So in the chat, I mean, I just spotted there was a question, and the question is already answered. I mean, that's is there a particular reason why we don't use C0, this one, as a predictor? And that's and the answer is, yeah, you could, but it doesn't really make a difference because we also have beta naught, right? I mean, that's, so if we would basically set beta naught to 0, force it to be 0, only then C1 and or C0 and the corresponding beta 0 would have an effect. But basically, it's sort of potato. You either have the one or the other. And given that in linear regression, you do want to have an intercept because it makes much of the analysis much easier. If you have beta 0, then this variable here doesn't help anymore. And that's basically how you can think of it. But if you really insist on having it, I mean, be my guest, right? I mean, it's not going to hurt you. Good. Let me take a sip. So I already said, I mean, friends don't let friends use step functions, but friends do let friends use splines. I mean, splines are cool. I like splines. So in step functions, we just have these, well, a step function, right? It's basically just a linear. If your age falls within this bin, I just give one fixed answer. And if it falls in that bin, I give that answer, right? I mean, it doesn't somehow, it lacks expressivity, right? I mean, that's, if you look just, I mean, without reading the slide, if you look at this example here, we have the cut point at 50, but I just said it would be a really bad idea if you just have a step function. However, just on this data, just downsampled a little bit, oh yeah, on the left-hand side, well, this is pretty much the curve, right? Okay, well, I don't know if it really should go down here, right? I mean, that's okay. And then from 50 onward, it's relatively stable, and then it goes down a bit, right? I mean, we can argue whether this is the best possible model and we would like to predict with this, probably not, but this is already way more expressive than just one mean value over the entire bin. And that is already the main idea of a regression spline. We are going to take the idea of the cut points. So we have our input domain and we're going to place cut points. We're going to look at age groups, right? And per age group, we're now going to use a slightly more wiggly function than just the average, just the mean, right? So instead of fitting one high degree polynomial over the entire domain, we're going to fit relatively low degree polynomials over a number of regions, right? I mean, that's non-overlapping regions in our data. So it's step functions on steroids. Now, obviously, if the model that we use really would look like this, and now suppose that in approximately 10 years, I reach the mature age of 50, then yeah, what would be the prediction, right? I mean, that's, am I going to make this much, right? I mean, that's, or am I going to make that much? Or is it going to change, right? I mean, from on my birthday, it's also possible that, somehow this is not really the right model, right? We would like it to be like properly continuous, and that's and that is the second idea that we're going to use in regression splines. So we are going to use these bins, and we're going to have a relatively smooth function per bin, but we require not just cut points, but we require that these splines, these lines, are going to be knotted together at the same value, right? So now it's a cut point, and if I go to the next one, now it's continuous piecewise cubic. I require that at these borders they take the same value, right? I mean, this already looks much better, right? I mean, that's but it's not entirely what we want yet, right? Because it feels a bit weird that, look, hey, now it goes up, 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 down, and well, apparently on my birthday, I'm going to make, well, the gradient is going to change again, right? The sign is, I'm going to start to make more again, and then that feels a bit weird too, right? I mean, that's it would be a nice birthday present, but I don't know. Now we can require the values of the functions that we have on the left-hand and right-hand side of this cut point, not just to have the same value at the cut point, right? I mean, to have them knotted together, we can actually require them to be d minus 1 times continuously differentiable. That's where d is the degree of the polynomial, which means that what we require is that actually it just smoothly continues, right? I mean, that's so there is no non-continuous change at the cut point that we can avoid. And we can avoid, that is the key thing. That is the key thing, right? I mean, that's so if you have a so here we have a cubic we can make work. If you were to have a quadratic spline, right? So we forced to have a quadratic function here and a quadratic function there. Yeah, well, then it will be relatively difficult to have two functions left and right, right? I mean, that are doubly differentiable at the cut point, right? So they're not just at the same value, but the sort of the first. So the gradient means sort of it continues. That basically means we only have one function, right? We don't really have two separate functions, right? We force them to be the same. And hence, we only require things to be d minus 1 times continuously differentiable. So if we would have a quadratic function here and here, so degree 2, we only require them to be, well, the same at the level of 1 degree, which is like take the same value. If we now take a cubic function left and right, then we have a degree of 3 here, degree of 3 here. So we have d minus 1, so 3 minus 1, 2. Twice differentiably, continuously differentiably should be the same. So that means that same value and same slope. And that feels pretty good, right? So this is already goes to the direction, hey, wait a second, cubic splines sounds like a good idea, right? I mean, linear splines, let me just show you, bad idea. I mean, this is icky. I mean, that's quadratic splines, no, you can do it, but yeah, right? I mean, they're still gonna look a little bit like this. I say a little bit because this is 10 cubic still, but a doubly differentiable cubic spline, that's relatively nice and smooth. And that's I'll show you some other examples next up. Of course, we can go for quartic or quintic or whatever, right? We can push the dimensionality or the degree of our polynomial within each bin splines as far as we like, but yeah, do we really have to? And that's and the answer is going to be no. Because so if you have suppose that we just have one big bin, right, and we do polynomial regression with a high degree, it's going to be very squiggly. We can fit anything, right, but it's going to be difficult to choose all the parameters right. I mean, that's we're going to have very wide confidence bands. It's going to be icky. The power of splines is that we don't need to do so. But if we choose the cut points in a smart way, and I'll get to the answer in a second, that's Mohammed. If we choose the cut points in a smart way, then actually we can fit the data very nicely, smoothly, right, and sufficiently, but not overly squiggly, with just a small set of cubic functions. So reaching the same possible expressivity as if we were to fit a super high dimensional polynomial, right, super high degree polynomial, but we don't really need it. Just a set of relatively simple cubic polynomials is going to suffice. Now, the more regions we introduce, right? So right now we only have 2 regions, but suppose that I would draw a cut point here and here. Actually, let's do it every year, right? And every year I'm going to draw a cut point, and that's and for each, let's say, well, literally year of age, I'm going to fit a cubic function. I can do that, right? Nothing is stopping me, and that's well, let's say your tummy should already start to ache because probably I'm going to be extremely overfit, right? My model. It's going to be way too squiggly. I mean, I introduced essentially way too many degrees of freedom, but I'm still using relatively small, simple functions, right? And that's so if I now choose the number of cut points not too high and in the right way, then actually I can get away and fit my data really well with only a few cut points. How we do that, we'll show in a second. Let me quickly look at the chat because I saw a few questions and it's difficult to lecture and read at the same time. It's possible that underfitting we split X into tiny actually, so the first question, yeah, so is it possible that our model gets underfitted when we split X into tiny regions? Yes and no. I mean, it's a bit weird to say that it's then underfit. So the polynomial that you fit within a very small bin in which there is very few data points, yeah, that polynomial is going to be, well, yeah, it's going to be overfit, right? I mean, that's basically, it's very difficult to choose it rightly. I mean, that's, it's not going to be underfit. It's rather going to be overfit. And because we're now going to combine many of those already somewhat overfit polynomials, I mean, the overall model is also going to be very overfit. Basically, you're going to be super squiggly around all the data points that you have. Underfit is the other opposite. And that would be that if, let's say, for data that we're currently looking at, and you just fit it with a linear function. That's well, what we're now looking at, right? These data points is not really a linear relationship, right? I mean, that's whether it's now cubic or quadratic or what it is, but linear it is not. Then the question on how to choose the regions, we'll get there. I'm going to skip that question for now. Yeah, then a question by Marco. Wouldn't the quadratic spline have the same value and same slope at the cut point? Yes and no. So let's just pretend that we fit a, oops, where are we? Okay, there's my pointer. A quadratic function here, right? I mean, that's, and it's easy to imagine that, I mean, I just have a quadratic function that looks like this, right? Just a parabola. And I can also have, let's say, well, you could even say the same parabola right here. And if I require them to, so if I don't require them to be in, let's say, knotted together at all, it could be that this one goes here and this one goes here, right? So this one and this one, left-hand and right-hand side of 50, not connected at all, right? I mean, that's, if we require them to be at least one time continuously differentiable, that would mean that we have this parabola, and now the next one should at least have the same value, right? I mean, that's, but the slope that we have here at the cut point itself, no, that is not going to be continuous, right? I mean, that's because it's only continuously differentiable once. Now, if we have a quadratic function here, now I need to lift this one up. So it's going to be here. And so the slope here is clearly going downward, right? I mean, that's now the only way, if I now require that at this point, it's going to be doubly continuously differentiable, right? So it's the next, the quadratic function that I can choose here, it needs to not only start from the same point, but it needs to continue at the same slope. Well, there's only one thing that I can do, namely basically continue the previous one. That's the only thing I can do.
Actually,
so basically,
no.
I don't have any degrees of freedom left anymore.
You could go down and then up again with a parabola.
Okay, if you invert it, yes. Yeah, technically, okay, that is technically possible. But
d minus 1
degrees of freedom that you have become, well, and almost zero. Let's call it that.
But doesn't d minus 1 mean, like, if we have d equal 2, so quadratic, doesn't d minus 1 mean we have the value equal, which is like the 0th derivative, and also the first derivative, d minus 1, first derivative, so slope equal? Because there's also like an example in the book actually with linear splines.
That is true, yeah, that is true. Let me see. I always think about it more in the way that I just said, but I mean, that's technically, that sounds correct, yes. That, but it also means that, yeah, so basically in the story, nothing changes so much because basically quadratic is still a stupid idea. So indeed, so if you have like this, then you can continue, well, either with the same parabola or, well, the downward one. And then for the next one, it would be the upward one, and so on and so forth. Basically, you don't have enough, let's say, well, expressiveness, wiggliness, and that's and that is the major point that you do get with your cubic splines. That you don't just have the same knot, you can also have the same slope here, and because of the third degree that you sort of left, you can do some magic in the remainder bin. Yeah. So yeah, good point. Good point.
I mean, my question was about the rule how splines work, right? Even if it's not like useful or whatever, but I mean, technically a cubic spline also has the same curvature, right? So the second derivative then at the cut point.
Yes. Yes.
Okay. Yeah.
Yes. But yes. But at least there you don't just have like with the parabolas. It's not just, well, if this is the one parabola, then the only one that you can fit is this one, right? I mean, in the quadratic case. Now at least you have a whole number of possible cubic things that you can still fit. But, good. Let's see. Let me continue. Won't really lost be different. Yeah, Dennis, I'm going to postpone your question, and that's not just because it goes a little bit too far for what we have currently on the slide, but one of the methods I'll be discussing in a bit, well, that should take away all these questions and these worries in a very nice way, and that so I think that didactically that will be a better fit. Good. So unless we have specific questions for the regression splines currently on the slide, then type them now. I'm just going to take another sip, and I'm going to continue. Oh. Good. Okay. Yeah. So that blah blah. Now let's see. The next. So what was now the nice bridge that I built in the first part of the lecture? I mean, up till splines, I was basically saying, okay, everything is just linear regression, right? It's just multiple linear regression. I mean, that is that, right? I mean, that's and we just transform a simple linear regression into a multiple linear regression where we essentially apply some functions on our input variable, right? Or into input variables, because it also works for the multiple, the multivariate case. Now these functions, we call them basis functions, right? I mean, it's not in the slide, you will find it in passing in the book, right? I mean, I'm already going a little bit ahead to one of the other chapters, but essentially what we do, we apply some function on the input variable, and well, we may use multiple functions, and we take the outputs as if those are actually our predictors, right? And that's this works wonderfully well directly for the polynomial regression, because then the functions are clearly, it would be, well, just x itself, it would be x squared, it would be x cubed, right? I mean, clearly those are functions, right? With the step functions, well, clearly, right, we had these indicator functions, these values, these c, right, I mean, that took a value or not. I mean, they were very clearly in your face, they were functions. Now, in splines, it becomes a little bit more convoluted because, yes, within a bin, for example, here, you can kind of reason, okay, we have these functions again, right? I mean, that's, but what now between bins? And then we have these constraints that they need to be connected and doubly or whatever, I mean, triply differentiable. That well, turns out if you actually do the math, I mean that it comes down to exactly the same thing. It's just that the set of functions that you're looking at, literally right now, is a little bit more complicated than in just plain polynomial regression. But there's nothing that should really truly scare you. I mean, that's now if I just put it formally, that if you have a regression spline of degree D with k knots, together they form a vector space of this. What does that mean? I mean, that's the vector space of, in this case, is cubic splines, right? Cubic splines, 3 plus 1 is 4, k knots. So k has this thing has k plus 4 dimensions, this vector space, right? I mean, those are essentially the functions that we need to play with. I mean, that's And now let's skip this part for now. The basis function we're going to be looking at, the function is going to be 1. That's just our intercept, right? This is the bias term, right? That's we have x. Hey, we have x. We have x squared. Well, obviously, right? We have x cubed. It's a cubic spline after all, right? I mean, that's so these 4 together would be just plain polynomial regression, right? I mean, that's or plane for up to the 3rd degree. And then we have these weird h functions with these zetas, right? I mean, we have zeta 1, zeta 2, all the way up to zeta k, you know, or zeta or eta. I mean, I always forget with the squiggly. What are those? Well, those are just, I mean, if you rewrite things, relatively convenient way to specify that we don't just have polynomial functions, but that these polynomial functions, they need to satisfy some properties at the borders, right? So basically per border, we're going to have such an h zeta, and that's going to specify that we want to have them connected in the right way. That's, I'm not going to walk through this because this is really something where just read it from the book. I mean, that's walk through an example and all should become clear. I mean, that's the core thing that I want to point out here is that everything is just plain linear regression, just multiple linear regression, right? The only thing we've been doing so far is just we take x and we apply a function to it. And we do this for multiple functions, and then afterwards we just do plain regression. So even splines is just linear regression. Although in the end we get something way, way cooler. I mean, not, let's go to the next example. I mean, not, still the same data, but we have chosen the cut points. Now we have 3 cut points here, right? 3 knots in that, and we have just, I mean, I should redo this plot. Just look at the blue line for now. I mean, that's just at the blue line. I mean, that's so that's this one, right? I mean, that's what we see there is that, hey, this actually fits the data quite well, right? I mean, that's I would be quite happy if let's say if I would give you just a scatter plot, and I would ask one of you if it would be an oral exam, okay, please draw, let's say, an appropriate curve, right? You would draw the blue line. I would be reasonably happy, and that's now. If we, now it's out of the exam question, but if we now look at the confidence band, right, around it, you see that actually here the confidence is not that great, right? I mean, that's because in this bin, we don't have so many points. Plus, what are we doing? We're doing actually something relatively stupid here. While here we have enough data points to fit a cubic function, plus we have the constraints that we should meet the same value of that is fitted here and the same value that's fitted here, and it should be differentiable and all that jazz, right? I mean, that's so in this bin, we don't have so much freedom to just choose whatever cubic function we do. On this one, because it's really at the border, we don't just have few data points, so we can't really fit the thing so well, but we have no idea in which direction this curve should actually continue. We have exactly the same problem as we had earlier with polynomial regression, right? And that, oops, things just go off. With polynomial regression, at the edges, we don't know in which direction it should shoot off, right? Should it go up? Should it go down? We have no clue, right? I mean, that's, so we have a huge risk of overfitting at these boundaries. And this is what you then also see if you do the analysis appropriately, that the confidence regions, I mean, here at details, I mean, they look horrible, right? I mean, that's, we could just as well throw away any prediction in the right and left-hand bins. Now, you could say ridiculously simple idea, or I mean, hack or fix, is basically say, you know what? Here in these, let's call them the inside bins, we do fit this cubic function. And this one is already constrained, again, because they need to be knotted and differentiable and whatnot. But you know what? In the outer bins, we are not going to fit a cubic function anymore. We're not even going to fit a cubic of, not even a quadratic function. We're going to fit a linear function, right? Because really, what else can we do, right? I mean, that's, and if we follow up on that idea, that is exactly what you get now with the red line, right? And as you can see here in the middle part, it's almost the same as the blue one, right? I mean, that's, but here, now it's just a straight line. This is just a straight line. And that actually makes a lot of sense because, well, a straight line, there's not so much that we can do wrong, right? I mean, you can't overfit that badly in linear regression. I mean, that's, so yes, this line, the red line here is a straight line. That's, And that is the big difference between just plain cubic splines, where we fit a cubic function in each of these bins, right? I mean, that's under, again, the knotting and the differentiable stuff, right? I mean, that's and the natural cubic spline, there's nothing natural about it. It's more like the linear ends cubic spline, but that just sounds bad. It's just cubic splines in the inner boxes and a linear spline in the outer ones. While, of course, making sure that the slope and everything here is fitted, right? I mean, that's that it sort of nicely continues and it doesn't all of a sudden shoot off in the wrong direction, right? I mean, that's I think. I mean, when I first read it, like, okay, but wait, this is too easy, right? It can't be that easy. But it's really one of those things that makes it tick wonderfully well. And you can also see this already, that the confidence bands here, they look already much better for the red one than for the blue one. Right? I mean, that's, of course, they are much wider here than over here. Yeah, because the data is sparse. We almost don't have any data points here. So we can't really be really certain about any prediction here, right? And that's, we simply have too few old people that make money. But at least we don't have these weird bumps in that we can reasonably well predict in these areas. Yeah, to put this formally and do a bit of PowerPoint karaoke, cubic splines have high variance at the boundaries of the value ranges, because, well, they're only sort of being constrained here on the left-hand side, right? On the right-hand side for the blue one here, the left-hand side for the blue one here. And by now taking away that it can sort of shoot off in any direction, by just forcing this now to be linear, we all of a sudden avoid overfitting. So that's by just doing this with linear splines, we have natural splines, and that's that. Then you may ask, let's see, yeah, so what if the data is sparse in, well, let's say here, right? Let's say we have lots of data in this, but we don't have any data here, right? I mean, that's, could be, I mean, that's, well, that is not so much of a problem. Basically, the trick, how should I say this? Let me ask it as a question. I mean, that's, how free am I to choose any cubic function within this bin from 40 to 60? And can I choose any cubic function? No. Right? The answer is no. I mean, that's because whatever function I choose, it needs to be, well, knotted with, well, the one I have here on the left-hand side and knotted with the one that here on the right-hand side. So I don't really have all my, let's say, well, degrees of freedom, right? If I put it formally, right? I mean, that's, I can't choose all my coefficients completely freely. So in a way, you could say that if you would somehow, well, I don't know, you had the Christmas break, right? Let's say you were super bored and you put every possible cubic function in order, right? I mean, you enumerate them, right? You write them down from left to right, all of them, right? I mean, that's, and then after you've done that, after you're done with that, it's going to be, well, infinite, right? I mean, that's, so it's going to take more than justification. And then you're going to just mark which ones are still admissible given the constraints on the left and right hand side. That will be way, way fewer, right? I mean, that's, so in that sense, the chances that you're going to be overfitting here with having a left and right hand boundary is going to be much smaller than if you are not given these constraints, right? I mean, that's, in a way, this bin on the left and this bin on the right gives you sort of information, say, for free, right? I mean, that prevents you from overfitting within this bin. Now, this also brings to the point that we saw earlier. If we have too many bins, and this was basically the question that Mohammed asked, I mean, that if we, let's say all these bins are super sparse, right? I mean, that, so then obviously we can't fit a good cubic function in any of them, and nor can we fit, let's say, well, a whole good spline over everything, right? Because we simply have too little data to make any sense of it. And then this is not really going to help. But as long as, well, only few, and I can't really quantify this any better, of these bins are sparse, doesn't really matter. Doesn't really matter, right? I mean, that's basically the day is being saved by this knotting. But I hope that answers your question, Thomas. Okay, so now let's make the bridge again from all the way from multiple linear regression. Then we had these basis functions, right? For cubic splines, the basis functions look like this, right? This is basically what you're doing your regression over. And what now for natural splines? Because now we do this linear thing here, right? So it doesn't look exactly like this anymore. And that's now for natural cubic splines, your set of basis functions then look like what we have on the slide here. I mean, that's I'm not going to walk it through because there's all these, you know, lots of zetas again. I mean, that's but essentially, well, we have the NS1. We just already saw this. Look, this is the linear one. Then we have for different degrees. I mean, that and this one now fixes in a nice way that it needs to be, let's say, at the same slope, yet we do allow linear there. That's in practice. This set of basis functions versus, now I'm going back one slide, this one, so the natural one, has fewer degrees of freedom because we can't just choose any cubic function here anymore. We can, well, in a way, only choose that cubic function that actually is a linear function, right? We just took away some of the freedom. And because we took away freedom here, well, we also take away freedom here. And because we take away freedom, well, and so on and so forth, right? And that's, so that sort of trickles down. So a natural spline has a slightly lower degree of freedom than a plain cubic spline. And as a result, they have less variance because, well, there's more bias, right? Bias and variance trade-off. You all know this stuff. Good. Let's see. Let's go now to the that's actually, so the plus, I don't know if Professor Valero already explained. This means that, I mean, this is slightly more advanced stuff. I mean, don't think that I'm not going to ask anything about that in the exam. I can, and I may, and probably will. But the pluses are often topics that are best consumed from the ESL book, right? You will find most of the things also in the ISLR book, the main book, but the ESL book goes into much more detail in that. So just that you know. Okay, now, how many knots and where do we put them, right? I mean, I think it was, was it Dennis who was asking it? I don't know, that's, one of you asked it just to go. I think, so the somewhat unsatisfying answer is that nobody really knows what is the optimal way of doing it until you found the optimal way of doing it. And that's, obviously, you cannot try every possible number of cut points and every possible location thereof. I mean, even through cross-validation, I mean, ain't nobody got time for that, right? I mean, that's, so typically what people do is that they choose either equidistant in the range of the input, and that's, so that would be, let's say, for every group of, let's say, 10 years, right? I mean, that's, we have then automatically k bins. Or the other way around, if you give me k, then I just split my domain into k equidistant ranges. You can also do this basically on the frequency of your data, such that you make sure that every bin has approximately the same number of points. It's not what this example here gives me. That's the third method. But for example, that if we see that, let's say we make sure that we have at least, or we have exactly 100 data points in every bin, right? And over 100 data points, we can perhaps reasonably fit a cubic function. So that would mean that where we have much more data, we have perhaps more bins, but it's also fair, right? Because there seems to be a lot of action there. And if we have very little data, well, then perhaps a wider bin makes sense. There you still really have to choose k, right? I mean, how many bins do you want? And that's a bit tricky. I mean, we'll get there in a second, but okay. One of the approaches that people very often use in practice, and it kind of makes sense. I mean, it makes me feel a bit squeamish. I mean, I'm not super happy with it, but it does work in practice quite well, is to actually do this according to the quantiles in a data set, right? And that's, so basically you took the one cut point at the mean, right? I mean, that's, then you look, okay, what is then the, this is 25% of the data, 25% of the data, 25, 25, and so on and so forth, right? I mean, that's, so it's related to the equifrequency approach, but yeah, quantiles is something that people are, let's say, especially in statistics, are quite used to with reasoning. In that, as a result, just with the equifrequency approach, where you have a lot of data, you'll have more bins, right? I mean, that, and well, that's hopefully where the action is. The downside of quantiles is that if your data is multimodal, so if there's, let's say, different ranges of ages where you have many data points, then yeah, the quantiles are going to be a bit screwed up, of course, right? Because the mean is going to be in the middle, and then yeah, you basically will put the cut points where the action is least. and then the equi-frequency approach, where you have to choose how many points do you want to have in a bin, would make more sense, right? So if your data is multimodal. I can only say your mileage may vary. I mean, that's the best thing to do with these things is to plot your data, look at it, and well, try things out. Yeah, the number of knots is something that you can either choose by just meanwhile that putting licking your fingers, putting in the wind, and see what value comes to mind. However, we will in one of the next slides discuss a method that will, let's say, essentially automatically do this for you. It will take away the choice. And this also comes down to my favorite spline-based method, I mean, ever. And the nice thing is that the number of knots directly relates to, well, the freedom of your model. How squiggly can it be, right? This is already what we discussed. If you have many small bins, it can be really, really squiggly, right? I mean, that's the knots still constrain it, but it can be squiggly. Now, the nice thing is that we know how to compute the degree of freedom of a model. And then essentially this gives us a knob to turn to increase or decrease the degrees of freedom, and then determine how many knots do we have or should we have. And then we can also determine where they should be in that. So I'm not going to discuss with you where to put them, let's say by hand, but I'm rather going to do the second approach. I mean, that's the smoothing splines, which work directly on the degrees of freedom. Let me go to the questions again. Okay, Marco, your comment on H being correct, I will look at later. I mean, I'm not going to walk back right now. The straight line, yes, we answered. That we answered. Then the question by Luke. What happens when you choose your cutoff points to be equal to the number of X values? Does it even work? Yes. Does it generalize to a normal polynomial regression? Not quite, but exactly that. So put a cut point at every data point. That is what's going to be the, let's say, the magic of the method I'm going to be discussing in a minute or so. That's but it's one of those things that you know that if you have too many cut points, you're going to be overfitting. But if you're going to have basically as many cut points as you can have, then all of a sudden it starts to work again. It's one of those weird conundrums. In that, but we'll see how that works in a second. Then a comment by Danielle. Can it be understood as placing the knot at every percentage of data points? Yes, yes. So the quantiles approach is indeed, I mean, put a cut point at every 25, every 50%, whatever, right? I mean, that's of data points. That and the quantiles is really okay. You have n data points, and then you divide by k. That k knots. That gives you the number of points that you need to put in each bin, right? So if you start to count, if you order all your data points, and then you just put the first n over k data points in this bin, and the second batch of n over k in this bin, and so on and so forth, right? This is how the quantiles approach relates to the frequency-based binning. Good. Yeah, okay. I mean, I think that you believe that if we can do regression, we can also do logistic regression. And if we can do logistic regression, well, yeah, that's we can do a prediction. Great. Okay. Now, how do we choose the number of knots? Already said earlier, I mean, basically any choice of number of parameters. I mean, cross-validation is your friend, right? I mean, that's so here, same thing as well. I mean, that if you plot for, well, this is then for a natural spline, I mean, that's the mean squared error on the data that we just saw. And you see that if, well, the degrees of freedom is way too low, right, then bad error, and otherwise it very quickly just flattens out. So that also shows that if you have a degree of around 3, this is, I mean, I would say 3 is good, maybe 2 already, because somewhere around that. And you can also see that actually between the natural and the cubic spline, there's not so much difference, right? I mean, that's even though the cubic spline, it will taper out at the ends, right? We saw that. That's why we like natural splines better. But if you just look purely at the error, there's not so much difference, right? It's also because the error doesn't take into account the confidence bands. So always like natural splines better. So coming back to the question that Luke said, okay, if we choose the number of cut points really high, I mean, does it become just polynomial regression? No, it becomes better. And yes, we can put cut points everywhere, but it's not polynomial regression. And that's the weird thing is, and this is actually what I already sketched earlier, that even though we were to have many cut points, and we have hence many bins, and hence we fit many cubic functions, because we have to tie each of these cubic functions together, we don't have so much wiggle room, right? We can't place them completely arbitrarily. I mean, that's each of those cubic functions is essentially constrained by its neighbors. That's and in polynomial regression, we don't have that. So in this particular case, if we fit a polynomial with a degree of 15, right? I mean, that's so that goes from x, so age, all the way up to the power of 15, right? I mean, and we fit this, we can do this, of course. We get a fit that looks like this, like the blue one. And well, while in this area, this looks pretty good, I mean, this doesn't make any sense, and this is also really bad, right? I mean, that's and especially like the tapering off at the ends, right? What we already discussed. I mean, that's don't trust your polynomial at the ends. I mean, that's now, if we take a natural cubic spline and we force it to have 15 degrees of freedom, and we place the knots that we get from this appropriately, then we get the red line. And perhaps it's a bit too squiggly here, right? I mean, to my liking, because degree of 15 is ridiculous, if you ask me. But it overall is a much better fit than the blue one, right? So these are both models with a degree of freedom of 15, right? But I would say the red one is superior in that. So is it the same? No, not at the same degrees of freedom. However, here we're not yet at a cut point per data point, right? We'll see that in a second. Okay, good. Let's see. Now we go to this. Well, let's have a cut point everywhere, right? Everybody gets a cut point. That's very Oprah-esque. How should I say this? If we put a cut point really everywhere, then yeah, and just basically for one point, there's little point in fitting a function on one point, right? I mean, anything goes, right? I mean, that's so the weird thing is at the moment we have n cut points, we don't have to choose the shape of the function that we fit within a bin anymore, because anything goes, right? I mean, that's if we have multiple points, we should choose a function, but if we just have one point, it doesn't really matter, right? I mean, that's now, so that is a bit of a conundrum in your head, but we do still have, if we now have somehow fit some line, right? I mean, at this around this point, at this cut point, right? That's then we do still, and we go to the next. So we have the cut point at point 1, right? This is, let's say, point 1. I can also just, no, actually, not just, let me just wave my hands. I mean, that's the cut point at point 1, point being, for example, here at the top of my pinky. And this is the cut point at the adjacent point, right? Let it be a bit lower. And again, at my pinky. Okay, my finger's not on my thumb. Okay, then you can actually see it. I mean, that's so. Oh, so yeah, now yeah, you can see. So there should be a line somewhere between those 2 points, right? I mean, because they need to be connected. They need to be differentiable, continuous, and everything, right? I mean, that's. But essentially, by now drawing a line over every point, right? I mean, that's. Yeah, I don't really have to choose the should I say this? I don't have to choose the shape of the function within a bin anymore, right? It's just a line, and I can just draw an arbitrary line, right? And that sort of comes for free. That means that all of a sudden we are non-parametric. That's essentially what I'm saying, right? I mean, any line goes. We have infinitely many possible lines, right? I mean, as long as they go through the points and they're differentiable and stuff, right? I mean, that's now, if we have this, then we can still do prediction. If we can do prediction, then we can compute residual sum of squares, right? I mean, that's. But now we can ask the question: out of all lines that we can possibly draw through all points, right? I mean, that's or as well as possible to these points or these cut points. Many of them will have the same or approximately the same residual sum of squares. But we can also look at the squiggliness of the line that we draw through all these cut points, right? And what we don't like about polynomials of the high degree is that they become very squiggly, right? I mean, that's so suppose that we now enforce them to be as well, a little squiggly as possible, but as much as they need to be. That idea is exactly what smoothing spline stands for in that sense. So we now have at every essentially value of h, we have a cut point. We want a line that goes through all these cut points at the same value and connected and everything, right? Just completely spline based. I mean, that's, and what we're now going to do, we're going to look at what is the second derivative of the fitted curve that we get if we draw through all these points, right? I mean, that's in the second derivative. Well, that is the squiggliness of a line, right? The more squiggly it is, right, the more often it goes from up to down and up to down, right? Well, the higher the integral of the second derivative is going to be, right? I mean, that's so the first derivative is just what is the slope, right? I mean, the second derivative is, okay, how often does the slope change sign? That's how you can think of it, right? I mean, that's squiggly lines change the sign of their slope very often. We don't want that, right? I mean, that's we would only when we really need to. So what we can now do is we can define a loss function as follows, where for every data point, we see what is the, well, the difference between the true value and the predicted value according to our squiggly line that we fitted over all the cut points, right? I mean, that's squared. Hey, this is RSS, plus a penalty term, a regularization term, which integrates over the second derivative of the fitted curve. So the squiggliness of the curve, right? I mean, that's, and now we have here a weight lambda, and this lambda now steers exactly the same effect as we have seen in ridge regression. And that's, it basically sort of gives a weight to lines that are more or less squiggly. If we set lambda to 0, well, we're just going to have that line that fits through our data, I mean, as perfectly as possible, right? I mean, it's going to be super squiggly. But if we set this to 0, if we set lambda to infinity, right, then, well, basically we try to minimize this error, and we set this to infinity. We want to have an as flat as possible line, right? I mean, that's so it's just going to be one linear curve. So if we start from lambda either infinity or 0, I mean, whichever end you want, right? I mean, let's start at infinity and let's start bring it down. That means that we have first a linear fit, right? I mean, that's and then it will start to become, well, increasingly squiggly up to a point that it becomes ridiculously squiggly, right? I mean, that's and now the only thing that we are left to do is to choose a good value of lambda. We don't have to choose the number of cut points anymore because we're going to have a cut point essentially everywhere, right? I mean, that problem is gone. We don't have to choose the shape of the function inside a bin anymore. The choice is taken away, right? We just want to draw an overall, I mean, as little as squiggly line over all the cut points. So the only thing we need to do is choose lambda. Well, how can we choose lambda? Cross-validation. Cross-validation, of course, right? I mean, that's now, yeah. So there's lots of connections that you can make. I mean, ridge regression. This is, yeah, that's very obvious, right? I mean, that's this has everything to do with shrinking, right? I mean, that's so if you think about it, I mean, you basically want to draw as many of the parameters as close to 0 as possible, right? I mean, that's because if you can think of, let's say, a polynomial with many of its parameters close to 0, yeah, that will just take the shape of that polynomial, right? I mean, that's how you can kind of think of it. I mean, that's so smoothing splines are essentially a shrunken version of spline width. Yeah, so you look at the second derivative. I mean, that just as an example here, if you have here the red, the same smoothing or the same spline we saw in the previous slide, right? I mean, that's 16 degrees of freedom. It's kind of okay, but a bit too squiggly. And we draw this now down to 6.8 degrees of freedom. How, trust me, this is possible, right? I mean, that's, we can even have, let's say, 3.14, I mean, just pi degrees of freedom if you want it. I mean, that's, but this happens to be the value that leave one out. Cross-validation says that's the value you want, right? I mean, that's, and if we now look at what does it look like, that's the blue line. And I hope that you agree with me. This is a very visually appealing line that seems to be a very good predictor of the relationship between age and wage, right? I mean, that's, it's not overly squiggly. It captures the general trend, right? I mean, seems like a pretty good bet. I mean, that's, and again, we essentially didn't choose anything, right? We didn't choose the number of cut points, didn't choose the shape of the function. we just use leave one out cross-validation to choose the degrees of freedom, every thing just came out of the box, right? We're not, okay, so how did we do that? I mean, this black magic. Lambda, well, shrinks the spline that we already established. I mean, that reduces the effective degrees of freedom. That, how can we compute the degrees of freedom? That, we've already seen this. I mean, that in rich regression, right? I mean, that but essentially what we want to look at the trace of the, well, not the hat matrix directly. I mean, that's but basically the trace of the lambda matrix here. I mean, that's there we have it. So I'm not going to walk through this again. This is also going to be an assignment. I mean, that's so, I rather just want to smooth over the main ideas. But we can compute for a given value of lambda what is the actual, let's say, the amount of freedom that the smoothing spline has. And that's cool, because in theory you can do this for every possible value, right? I mean, that's so that allows us to say also the other way around. If I want a smoothing spline with so and so many degrees of freedom, okay, then there you have it, right? I mean, that's so we know what the value of lambda should be. That's how can we now choose lambda? Because neither you nor I want to choose it by hand. I mean, I don't know what is a good value, 1, 2, 3, right? I mean, whatever. I mean, that's now the nice thing is there is a connection through, let's say, the standard linear regression machinery that we can use the leave one out cross-validation trick, right? So in a few lectures ago, I mean, you saw how you can use leave one out cross-validation to determine the generalization error, right? Basically estimate the test error, what's going to be the test error for your model. And there was this very convenient way of computing the leave one out cross-validation essentially in one go for RSS, right? I mean, that's now we can reuse this directly here. That's very neat. I mean, that's so for a given value of lambda, the cross-validation value is going to be looking like this. And then it's just a sum like that. We need to just have this matrix, and there we are. Just look at the diagonal of it. So that means that we can just try this one out for different values of lambda, right? I mean, that's this gives us then an RSS value. We choose the one with the lowest RSS value. That is our favorite lambda, right? And there we are. And that's essentially any piece of software that can fit splines, and this is completely standard, will do this for you, right? I mean, that's which is good for you, I mean, after this course, because then you can just apply it, right? I mean, that's what is bad for you is that right now you will need to study this a little bit and see how does this now work. Where do we get this degree of freedom? Where does it now really come from, right? I mean, there's a reason why I don't go into too much detail here, because I want you to study it. I mean, that's some things you just need to see by yourself rather than be pointed at it. But let's say the take-home message so far is smoothing splines. Hell yes. Smoothing splines are a very, very nice tool, right? I mean, that's, if you want to do regression, this should be one of your go-to tools. Okay, good. Unless there are really pressing questions. I'm now going to continue with the, method number 3 and 4. And I need to keep track of time, and that's I'm going to go slightly over time, I'm afraid. But the third method that I wanted to discuss, the main method, right? I mean, the third main method, that's going to take very little time. That's that is local regression. And why is it not going to take so much time? Because it's a simple concept. It's powerful, but it's very simple. I mean, it's easy to explain. So we already know that k-nearest neighbors is a pretty good way for doing prediction, right? I mean, that's you can even do regression based on it, just by taking the average, right? I mean, that's however, we can actually do this a little bit more smartly. I mean, that's and if we do this a bit more smartly, it's not just k-nearest neighbors based regression. It is, we call local regression, but I mean, potato. I mean, it's in the end the same thing. I mean, that's now what are we going to do is that for a given query point, right? So what we now want to, so I want to know what is the value of y for this value of x, right? I mean, that's what I look up is what are somehow the k nearest neighbors of my lookup point, right? Those are all the orange ones over here. And what is now going to be different compared to the k-nearest neighbor regression you've already seen, I'm not just going to take the average of all the orange points, right? I mean, that's one you've already seen. I'm actually going to take these orange points and I'm going to fit a polynomial on it, right? I mean, that's I'm going to just fit some model on it. I mean, but only on the orange points. I'm going to ignore the rest of the data, right? I mean, so this is somehow, you could say, where you have cubic splines are basically a cubic like polynomial where you only look at, let's say, a fixed bin, right? I mean, that's you're either in this bin or you're in that bin, right? I mean, so it's sort of the connection from polynomial regression to step functions, then you're at cubic splines, right? And what we're now doing in local regression is that, okay, you know what if there are no bins, right? I mean, we don't look like just within a bin, but for every query point, we just simply create a bin by considering its k nearest neighbors, right? Now, just taking the k nearest neighbors is a bit stupid. Why? Well, this is again the same thing as we're doing polynomial regression, and then at the tails we don't really know where things should go, right? Because we don't have data. Exactly the same thing here. If we only look at the orange points, I mean, we have much more confidence about where it should be around here in the middle. So actually, let me just go to here. This is a better example. I have much more confidence, let's say, in which direction this line should go here in the middle than I have here at the end. Because these points, for all I care, they don't exist, right? I mean, that's so perhaps this line should go up or down, or I don't know, right? I mean, flatten out. But here in the middle, I'm quite confident. So this is the second trick that you do in local regression. And that's you don't just blindly use all the k nearest neighbors, and blindly I mean use them, let's say, equally, see them as equally important. No, you take those points closest to your query point as important. That's what this green blob here, this bell curve, represents. These points here are important. These points, I don't really care so much. So in other words, what I'm going to do, I'm going to fit a function over these orange points where I don't really care so much if I make more error, let's say, on the points here at the end than I do here in the middle. Makes sense, right? I mean, that's there where you have, where the action is, that's where you want to fit well. And that's okay, good. Now the what is the result? What are you going to get? Let me just go back one slide. I mean, that's so the true generating curve is the blue one, right? I mean, that's and if you now look at the curve that you fit through local regression, so basically what I now did, or what somebody who plotted this, for every possible value of x, we look at the k nearest neighbors, or we do the local regression thing, see what is the prediction, and then the orange-ish curve, that is then the prediction. And as you see, it actually fits the blue one quite well, right? I mean, that's even though it only always takes a local approach. Now, the curve that is actually fitted at this point was, in this case, this linear thing over here, and that's and the green thing is the weight. So these points I don't care so much about. These points I do. Okay, now how do we choose how many points and how do we assign the weight? And now things sort of go a little bit beyond just plain k nearest neighbors. In k nearest neighbors, we would take all the k nearest neighbors and we assign them all the same weight. So basically the green function would just look like this, right? I mean, that's just a block, and that's that. Now, what we want to do is we want to remove the influence of the border points as much as possible. So we want to have something Gaussian-ish, right? I mean, that's now, what is the problem if we use a real Gaussian? So here I conveniently drew a Gaussian. I mean, this is the blue one. A Gaussian is a function with what we call a heavy tail, right? I mean, that's so even though the majority of the probability mass will be at the mean, in this case at 0, right? I mean, that's and then it has a certain variance, but you see it sort of very slowly goes down, right? And actually, even though it seems that it sort of hits 0 here, it doesn't. There's always some non-zero probability left, right? I mean, it's only really completely in the limit, it will reach 0, right? I mean, that's but in practice we're never in the limit, right? I mean, that's So that means if we were to use a Gaussian, unless we're really careful, and that's well, actually careful if we choose the coefficients really pedantically, then actually we would always use all the data points somehow. And that we don't really want, right? Many of them will have an almost zero probability. I mean, that's, but so what we want is a slightly more aggressive shape, right? One that actually hits zero. And that's why we can use, for example, the TriCube or the, okay, there was somebody who asked a question with a slightly more Russian sounding name. Perhaps you know how to pronounce this, Epanechinikov. Anyway, you need a function that does assign a lot of weight around zero, right? So close to the query point, and then at one moment essentially goes to zero. The TriCube is very often used. I mean, that's, as you see, it replicates the idea of a Gaussian without the heavy tail. Such a function, and I'm going to now skip over this very quickly because we're going to look into this in the next lecture again. We call this a kernel function. Basically, what it means is that we apply this function to every, so we apply it here, and then every point gets a weight according to this function. And this weight we're now going to use in the importance in the learning. So kernel functions, I mean, now you've seen the name, right? I mean, that's not so important. Well, until next week. Next week it's going to be important. Okay, now suppose that we've chosen this function. Being a trikernel, you may still think, for all I care, about a Gaussian. And that's, I'm not going to be upset. Now, a Gaussian, because the Gaussian is easier to think about, right? A Gaussian has a variance, right? I mean, the mean is going to be zero because we want the majority of the mass to be here at the query point, but it has a variance, right? I mean, the wider the variance, the wider this blob is going to be, and the more points are going to be included, right? I mean, that's the more points are going to be included with all relatively little weight, but the more they are, right? The smaller the variance, the fewer points are going to be included with a lot of weight, right? Intuitively, I hope that makes sense. I mean, that also holds for these other functions, for this TriCube, for the Epanechinikov, or whatever way you pronounce it. Now, this parameter, I mean, well, it goes under many different names. I mean, but you can call it the width of the kernel, or you call it the span of the kernel. I mean, there's a number of different things. That is a parameter we do need to choose. How are we going to choose that? Hey, let's try cross-validation. Yes, that is actually a good idea. I mean, that's, but essentially, you want to be sufficiently local, but not too local, right? I mean, if you choose it too aggressively, you only fit on, let's say, the two closest nearest neighbors. You're not going to be able to fit a good line, right? I mean, that's really figure out what is going on here. I mean, that's whereas if you choose it too wide, you just have global regression and you fall into well, the standard problems. Yeah, so this I'm going to mostly skip. I mean, that's the kernels. Maybe we'll revisit this next week. I mean, that the important part, though, is actually what I do want to point at: a large value of lambda. I mean, that's so this is the span, right? I mean, that's essentially as related to the span. So the wider the span, I mean, well, the more bias, and hence the lower the variance. But if you have a very small span, well, you can do basically anything, right? Because you only have to look at an individual close point, and you have lots of degrees of freedom, essentially. So then you have a very high variance. So again, bias variance, I mean, that's a trade-off. Good. This I'm going to skip. And now I want to have spent the last 5 minutes or so on GAMS. That's generalized additive models. Generalized additive models are essentially what we've seen so far, just slightly different. So this is what linear regression looks like, right? I mean, to us, I mean, that's we have, this is going to be the value of a variable x1, I mean, so the ith sample for x1, the value of x2 ith sample, and so on and so forth, right, up till the bth predictor. And we have all our betas for that. I mean, that's great. Now, what we've been doing so far is basically not using either directly the value of x, but somehow, well, faking x into, well, squaring x, cubing x, right? And just play pretend that we just have an additional new predictor. And we're going to call it x again, even though it was actually just x1 squared or x2 squared, right? I mean, that's what we've been doing so far. So we have been actively choosing the basis functions, right? I mean, that's that we're operating under. We can also say, you know what, screw it. I don't want to choose this myself. I want to learn this, right? I mean, that's and I don't want to learn this, but I want the machine to learn it. I mean, that's and then actually you would rewrite it as follows. So we have a beta naught. We always have an intercept. That is fine. And essentially, then I want to have some function over x1, some function over x2, and so on and so forth, right? And that is that. And I don't want to have a weight anymore, right? I mean, that goes into the function. The function can have its own intercept, right? I mean, that's and if this function now really wants to be, if it's really important to take, let's say, the square of x1, sure, let it learn it, right? I mean, that's don't bother me with it. And if x2 needs to be cubed, sure, go ahead, learn it, right? Don't bother me with it. I mean, that's I want it to be non-parametric. Okay, well, sure. How can we do this? Well, the nice thing is that these functions, if we want to learn them non-parametrically, we can use splines. We just saw that, I mean, these smoothing splines are non-parametric. Maybe we can adapt their wiggliness. They're pretty cool. And they can learn cubic, quadratic, whatever shapes, right? I mean, that's that's essentially what we're now going to do. We're going to try to model wage with an intercept, some function over year, some function over age, some function over education, and whatever noise. I mean, that's and this brace should not be here. Okay, what we're now next going to do is that we're going to set the degrees of freedom to 4, 5. I mean, it's magic. I mean, we chose just magically. I mean, that's education is a categorical variable, right? So we just use dummy variables. You know how this works in regression, right? We've seen this, I think, 3 lectures ago at the top of my head. What do we now have? I mean, that's what are these functions, f1, f2, and f3 going to look like? I mean, that's well, they would actually look like this if we train them appropriately. So there is going to be over a year, right? I mean, that's there is going to be some. Oh, you could. It's not linear, right? But it's relatively linear dependency between year and the predictive power of year, and that's if you look at age. Well, age definitely has a very strong nonlinear component, right? I mean, that's so learning in this case, this spline, right? This is, well, let's call this quadratic, right? I mean, that's just for the heck of it. So basically here we would like to have had a quadratic function over age, but if we didn't know it, this would be a very good approximation. And for education, there we see that somebody who didn't even finish high school all the way up to, I mean, has a PhD, yeah, clearly this has a positive effect, right? And also clearly nonlinear in that sense. Now I'll go to how to learn these functions in a minute, right? In that, let me see. So how should I lay this out? Yeah, okay, actually there's not so much difference to the next slide. I'm just trying to see, okay, what was the story I had in mind? Here we're looking at natural splines. I can do the same thing with smoothing splines. I mean, that's the tricky thing is that smoothing splines are a bit more involved to learn in this framework than natural splines, but in the end, I mean, we can do either. Now the tricky thing is that, let me actually go back. What we are looking at here, we have not one, we have 2, we have 3 functions, right? I mean, that's 3 functions that we didn't know beforehand, right? We didn't know their parameters. We didn't know that their shape even. I mean, that's that somehow here through black magic got fitted such that if I now go all the way back in this setup, they give a good prediction for wage, right? That's so for a certain value of year, certain value of age, certain value of education up, let's say it's year 2005. And we're talking with somebody about 40, and then well, in this range, okay, then we can learn this in our generalized model, right? I mean, this gives a good prediction. But we somehow needed to learn this function, and this function. Now, clearly they have some interaction going on between each other, right? Because if I have, let's say, a really stupid function here for year, right? Let's say it be flat, I didn't learn anything yet, or it's like, it's completely wrong, it goes in the wrong direction, right? I mean, that's, suppose that I was somehow I played foul with you and I force you to use the wrong function here. Then you might want to fix this with a slightly different function for age, right? Or maybe on education. Basically, you would like to correct let's say the lemons I gave you and the year function, right? I mean, that's so that is to say, if I just turn it around a bit, we want to learn all these functions ideally at the same time. We want to have the optimal set of functions at the same time. Well, I'm sorry, no can do. And that's not just because I don't want you to, or if I'm because I'm lazy. There's simply too many degrees of freedom. It's essentially impossible to learn the optimal set of functions at the same time, right? I mean, this is one of the things why deep learning is so popular, because that actually makes a very good attempt at this. But we're not teaching deep learning right now. So what we can do is something called backfitting. Backfitting essentially says, you know what? I'm going to start with some stupid initialization, or a random initialization of this function, of this function, and this function. And then iteratively, I'm going to refit. So basically, I initialize F1, F2, and F3. That gives you some prediction, right? A pretty bad one. I mean, that's a very bad RSS. I mean, and then I allow you to, while keeping, let's say, function 2 and function 3 fixed, I allow you now to learn a new function 1, right? Such that you minimize the error, which was very high because there were stupid functions, right? I mean, now, of course, you cannot learn everything there is to learn, right? I mean, with just year, but you will hopefully be able to improve the year function a little bit. Now, after you've done your best, right? I mean, that's, I say, okay, great. And that's, we're now going to fix the new year function, F1. And I allow you now instead to learn a better age function, right? Now, there's still some error left, right? Because you couldn't learn everything to the year function. I mean, that's, and maybe you introduce some new errors in addition. So what we're now going to do, now we're going to learn the age function. We're going to adapt it, and it perhaps now takes roughly this shape. Great, right? I mean, that's, and after you're done, again, this is the best I can do currently while keeping the F1 and F3 fixed, right? I mean, that's, then we go to the education function, and we do the best that we can do there, and so on and so forth. Rinse until, well, rinse and repeat, right? I mean, that's, so this is what's called backfitting. I mean, that, so we initialize as follows. So we have a beta naught. I mean, that's, okay, this is just to make sure we have the average, right? I mean, that's, and then for every j, so every function for every predictor that we have, right? I mean, that's, we're going to fit a smoothing spline or a or whatever we want to learn, right? I mean, that's, after we fitted this, we fix that one and we go to the next one. We fix that one, we go to the next one, and so on and so forth. I mean, that's, okay, in the interest of time, I'm going to skip over the details, but the most important part, we run until convergence. Until you can't improve any of these functions anymore, okay, then we're done, right? And that's, now, the nice thing is that in many cases, this is basically the same machinery you would be using for, well, solving a linear system of equations. And for that, we have a lot of machinery available. You've seen a lot of things like that already in MFE1, MFE2, MFE3, if I'm not mistaken. So there is very clear connections to, let's say, well understood mathematical concepts, right? I mean, that's, even if they're not immediately clear to you right now, like, oh my God, what is the Gauss-Seidel algorithm? This is basically just meant to be comforting, right? I mean, that's, we can do this. The most important thing to take from this slide that you're looking at right now is that learn one function while keeping the others fixed and just rotating around this, I mean, until convergence, right? That is the take-home message here. Good. Then, what do we have? The pros and the cons. Well, GAMs are non-parametric because, well, we can learn these functions using splines. Because it's non-parametric, we actually can fit any type of shape. We get very accurate predictions. Overall, the model is additive, right? We just have still F1 plus F2 plus F3. I mean, that's, this is a downside because if there's real interactions between X1 and X2, we can't model it. At the same time, it's also an upside because we can really see which predictors are actually how important, right? The flatter the function is for a variable, the less important it is, right? I mean, that's, the less flat it is, the more important it is. We can also look at the smoothness of these functions. Well, so that's, we can look at the degrees of freedom they have. And again, this tells us something, okay, is there really something going on, right? I mean, that's how linear, how nonlinear are they? That's, good. Let me very quickly go yeah, just that, actually, no, this is just an example. I'm going to put this on the site. You can read this yourself. I mean, this is basically rehashing what we've just seen. I mean, that's what I've just said. It's now 4:01, so it's really time to stop. I mean, that's please make it stop. That goes both from me and from you. I mean, that's good. So now, just very quickly recap. We've seen that with simple multiple linear regression as the engine, we can actually do not just linear regression, we can do polynomial regression. We can do step functions. We can do splines. Actually, we don't even need to do the whole polynomial business because we can do smoothing splines, right? I mean, that's if we want to do this now multivariately, generalized additive models allow us to essentially find a smoothing spline function per predictor and have the strengths of the multiple linear regression, right? So we can compute confidence intervals. We know how to optimize all the things while having non-parametric, non-linear functions over our predictors. So we gained a lot of power and hopefully a lot of insight in this one lecture today. So on that, I want to thank you for your attention. And that's if there's any questions or any comments, I mean, I'll happily go over them right after. But otherwise, I wave goodbye and hope to see you next week. Bye-bye.